Today, I'm going to tell you about this paper, Efficient Estimation of Pauli Observables by Derandomization. This is a joint work with Richard Kueng and John Preskill. The task that we study in this paper is the following. Suppose we're given a collection of Pauli observables O1 to OL. Can we efficiently estimate all of them on an unknown quantum state row? In particular, we're assumed that in the experimental lab, we have created some unknown quantum system of multiple qubits. And the goal is to be able to estimate an expectation value of a large number of Pauli observables, O1 to OL, up to some additive error epsilon. Such a task is very useful in a variety of quantum computing applications, which we will study at the end, which we will present at the end of this talk. So such a task has also been studied in previous works. In particular, in reference 1 and 2, the first one is by us predicting many properties of quantum system from very few measurement. And the second one is called scalable Bayesian Hamiltonian learning. These two papers have shown that for any few body Pauli observables, an order of log L copies of rho suffices to estimate any L Pauli observables up to epsilon error, up to some constant error actually. And the procedure only requires local measurements. That is, they could perform single qubit rotation plus computational basis measurement. And after that, after performing that for several rounds, we will collect a set of experimental data that allows us to predict the expectation value of any L few body Pauli observable. So few body Pauli observables are Pauli observables that are non-identity on only a constant number of qubits. That is, for example, Pauli X on the first qubit and tensor product with Pauli Y on the third qubit and tensor product with Pauli Z on the seventh qubit. So that would be an example of a few body Pauli observable. But you could also consider Pauli observables that are not few body. For example, a string operator of that acts X, like that have Pauli X on every qubit of your system, that would be a Pauli observable that's not few body. So in reference 1 and 2, they showed that for any few body of Pauli observables, you can estimate them very, very efficiently using only log L number of measurements as well as log L number of copies. However, they didn't tell us how efficient it is to estimate arbitrary Pauli observables. So for example, if we have a large number of these highway Pauli observable or string operator that acts on the entire system, can we achieve a similar scaling of ordered logarithmic in L? This is especially crucial for applications in quantum chemistry because most of the Pauli observable in quantum chemistry applications will be pretty high weight. In this paper, in a recent paper on information theoretic bounds on quantum advantage in machine learning, also by me, Richard Kueng, and John Preskill, we've showed that for any Pauli observable, ordered log L copies of rho suffices. However, the caveat is that this procedure requires a very quantum mechanical model. Basically, the algorithm have to act on all copies of the quantum state rho. So previously, in this setting, we only need to perform local measurement. That is, when we have a new copy of the quantum state rho, we only need to perform single qubit rotation and computational basis measurement. On the other hand, for this reference, for the third reference, we have to store all of these copies, like all copies of rho, log L copies of rho, in a quantum memory, and then perform some entangled measurements on this quantum memory. So basically, you have to entangle all of these different copies of rho in order to perform this protocol. However, if you can do that, then you can estimate any L Pauli observable. It doesn't have to be few body. It can be string operator. It can be Pauli observables from quantum chemistry application. But you can estimate all of them using only log L copies of rho. So very, very efficient in the sample complexity. So together, you can see that in the first two references, 1 and 2, they showed that you can achieve logarithmic scaling for few body Pauli observable using local measurement. And the third reference shows that you can actually achieve logarithmic scaling for any Pauli observable, but it requires quantum data processing on quantum memory that stores all copy of your quantum state. So the question that we wanted to sort of address in this work is whether we can improve the algorithm that based only on local measurement. The local measurement is very preferable experimentally because you only perform single qubit rotations, so you will have much smaller experimental noise because your gates is not going to be perfect. So if you apply like a deep circuit, it's going to induce a lot of noise that's not inherent in this unknown quantum state realm. And furthermore, it doesn't require you to store multiple copies of your quantum state in this external quantum memory and perform some joint quantum data processing. So it will be much, much more practical. And it would likely be immediately applicable in current experimental device. So that is the goal for this talk, basically trying to understand how can we improve upon these algorithms based on local measurement and try to tackle tasks where you have some Pauli observables that could be potentially higher weights. So before going into the algorithm proposed by this work, I wanted to review what the previous works have done. In particular, the literature on randomized Pauli measurements. So more generally, randomized measurement is a very powerful tool for extracting information from quantum system. And the key idea is based on the following. You simply perform some random evolution on your unknown quantum system, and then you perform computational basis measurement. So that was this framework called classical shadow proposed in this paper, predicting many properties of quantum system. In particular, it is also very useful for predicting few body Pauli observables. For that, what you do is as simple as following. So it's also known as randomized Pauli measurement. Basically, all you do is for each qubit, you randomly measure in X, Y, or Z basis. That's it. So you consider your quantum state. For each qubit, you just pick a random basis, X, Y, or Z, so parallel over all qubits, and then you just measure all of them. So for each qubit, you will get 0 or 1, and as well as the basis that you measure it. So for example, one realization of a randomized Pauli measurement is you measure each qubit in, for example, Y basis on the first qubit, X basis on the second qubit, X, Y, Z, Y, Z on the rest of the qubits. So that would be one realization, but you can imagine that different randomized Pauli measurement will produce different bases. And let us define some terminology. We say we hit a Pauli observable if the measurement basis matches with the Pauli observable OI. So for example, this measurement scheme where you measure YXX, YZ, YZ on each of the individual qubits, it will hit observables such as Y1, X2Z7, Z5, Y6, Z7, etc. But it will not hit observable like Z on the first qubit because you are measuring Y on the first qubit, so you're not going to measure Z on the first qubit. So that's just a terminology. So basically, we define this, and then subsequently we can define H of OI to be the total number of hits of an observable OI over multiple rounds of random Pauli measurements. So in random Pauli measurements, you will randomly measure in different bases every time. So maybe in the first time, the measurement scheme, the measurement basis will not hit the observable, but in the second time, maybe it will hit, and then so on. So you accumulate the number of total hits, and that's defined as H of OI. So in particular, if we measure every qubit in a random XYZ basis, then for any k-body Pauli observable, we will hit it with probability 1 over 3 to the k. Well, that was just a basic probability statement. So in particular, if we perform m different randomized Pauli measurements, then the expectation value of the total number of hits would be equal to m over 3 to the number of qubits that OI acts on. So this W of OI is defined as follows. So now suppose that we have sampled M random Pauli measurement such that for each observable OI, it will be hit by H of OI times. Then the success probability that all observable OI to OL will be estimated to at most epsilon error. You can show that you will be lower bounded by 1 minus the sum for all the observable, exponential negative epsilon squared over 2 times the number of hits. So the more hits you get for the observable, the smaller the exponential would be, and the higher your success probability would be. In particular, if you consider that all the Pauli observable have been measured for H times, then the failure probability could be written as the simplified form. So the failure probability is the probability that you fail to estimate all of them up to at most epsilon error. So as you can see, you only need the number of hits to scale as logarithmic in L over epsilon squared in order to measure all of these observables up to epsilon error. So now, as we have seen, the failure probability is lower bounded by this quantity. We can use the fact that when you perform random measurement, so when you perform random Pauli measurement, the expectation value of the number of hits would be equal to m over 3 to the number of qubits that this Pauli observable acts on. So as you can see, combining them in a rough sense, but you can do it very rigorously, you only need m to be of order log L max I 3 to the W of OI over epsilon squared to measure all of these Pauli observable to epsilon error with high probability. So the log L come from the fact that the summing over L is outside of expectation value. And then this maximization just comes from the fact that each of them would take in the worst case, take 3 to the K, right? 3 to the W of OI. And then this epsilon square is just the error that you incur. So now we can see that randomness indeed plays a crucial role in achieving the logarithmic scaling. The key question is whether this randomness is necessary or not. Could we actually construct a deterministic measurement scheme that can be shown to be at least as good as the randomized measurement scheme? So the key idea, and this is the central theme of this paper, and the key idea is to replace every random XYZ basis sampling by an at least as good as average choice. So how do we do that? So first, recall that in a randomized Pauli scheme, you go through every qubits in each parallel Pauli measurements one by one. So it could be represented by this rectangular matrix. So the red points is on the top left, and you just go sequentially scheming through all of it. And you pick the random basis X, Y, or Z. And then recall that we have shown that the failure probability is upper bounded by this quantity. So now what we do is we could actually also derive a similar failure probability upper bound. Okay, so recall that for this one, this is actually for deterministic measurement scheme. So that is, you have already fixed the basis, then the failure probability would be upper bounded by this quantity. But you can also consider a setting where where you compute the failure probability for a partially deterministic and partially randomized measurement scheme. That is, for some part of your measurement scheme, you already fix the basis, but for all the rest, it's still like a random XYZ measurement. You can also compute the failure probability upper bound on that, and it's given by this kind of convoluted formula, but it can actually be computed very efficiently. And then what you do is every time you wanted to throw a dice to pick X, Y, or Z, you choose the one that have the smallest failure probability upper bound. That is, you assume that the outcome is X. So now for the point, like this red dot point here, it becomes a deterministic basis. But all the rest, you still assume it to be randomized. You can compute the failure probability upper bound for that. And you can do so for X, Y, and Z, and you pick the one with the smallest failure probability. And basically what you can show is that it would always be monotonically decreasing. So that is, there always exists a choice X, Y, or Z such that it is, the resulting failure probability upper bound would be smaller than the original failure probability upper bound, where you consider this red point to be randomized. Because basically when what you're doing is you're replacing all the randomness by a deterministic choice. And you just continue that on and you use that algorithm to fill up the entire chart. So originally, you will have everything being a random XYZ with equal probability. What you do is you sequentially replace each randomness by a deterministic choice. And so the green parts would be the deterministic choice that you have made, and you do so by minimizing this failure probability upper bound. So at the end, you will result in a failure probability upper bound that is at least as large as the original failure probability upper bound when everything is randomized. So that is how you show that utilizing this derandomization procedure, you will end up with a deterministic measurement scheme that is at least as good as the randomized measurement scheme. So that is the rigorous guarantee that you can establish. And the way to establish is to prove the monotonistic decreasingness of this failure probability upper bound that we constructed. And furthermore, you can also show that by performing basic dynamic programming, the time complexity for performing derandomization is very efficient. It scales as nml, where small n is the number of qubits, big M is the total number of Pauli measurements that you perform, and L is the number of observables. And you can easily see that this is actually as efficient as the post-processing when you try to estimate the expectation value for all the observables. You also require this time complexity nml. So if you combine preprocessing and post-processing, you can see that asymptotically, you're not losing too much. You're basically not losing anything by performing the randomization scheme. So finally, let us look at some application. So this is an application for estimating ground state energy in small molecules. We consider the blue one, the derandomized classical shadow. We also compare with the original classical shadow, which is based on randomized Pauli measurement. We also compare it with this technique called locally biased shadow, which is a very nice idea where you try to learn the distribution for each qubit. So originally, you will do it uniformly if you don't have any knowledge. In locally biased shadow, they propose the optimization scheme to optimize the distribution for which you measure each qubit. So what kind of distribution over XYZ you wanted to measure. We also compare it with another state-of-the-art method called large degree first grouping strategy, where you try to group the Pauli observables into qubit-wise commuting groups such that you can measure them simultaneously. So this is the plot. So the x-axis is the number of experiments and the y-axis is the estimation error for ground state energy. And you can see that using the randomization strategy, it improves significantly upon the original classical shadow approach. It also improves upon these more recent approach. And on the right-hand side, we show the prediction error for a right range of different small molecules under different encodings. And you can also see that using the randomization scheme, you can indeed see quite a bit of improvement over other existing approaches. So note that we only compare with approaches that doesn't apply some depths before measurement. We only consider single qubit rotation and computational basis measurement. So those are the approaches that we compare to. So in principle, when you can apply some kind of rotation gates, some kind of entangling gates, you can also see improvement in the required number of measurements. However, including those kind of gates would also increase the noise, and there are some trade-off between the two. So here we're just focusing on a simple strategy where you just perform single qubit measurement and single qubit rotation, and you measure in a computational basis. Here is another application for simulating one-dimensional quantum electrodynamics. So in this application, we consider a variational quantum simulation of lattice Ringer model. So you have some parameters that you will tune to prepare some trial state for a fermionic field. And what you do is you wanted to be able to estimate the Hamiltonian variance. So the orange line is the derandomized version of the classical shadow approach based on randomized Pauli measurement. And the red line is the original classical shadow approach. And the blue line is some handcrafted scheme that a scientist created by looking at the Hamiltonian variance and try to cook up some good measurement scheme for measuring this Hamiltonian variance. And the y-axis is the number of experiments required to measure all the Pauli observable 100 times. And the x-axis is the system size. So as you can see, by performing derandomization, you can improve upon the original randomized Pauli measurement, the shadow approach, the red lines, up to a factor of 10, which is quite significant. So to conclude, we've shown that by performing derandomization, it can actually improve upon randomized measurements in estimating Pauli observables. And we've found that derandomization has actually not been fully explored in quantum computing. So one outlook is, are there other applications where you can show that by performing derandomization, you can substantially improve upon some original randomized scheme? And also another important future direction is to have a better mechanistic understanding for why performing derandomization can cause such a huge improvement. For example, here you see that there's 10 times improvement in the number of experiments. And here there's also significantly larger than 10 times, like 10 to 100 times of reduction in the number of experiments. So for example, here you see that the prediction error is smaller by 10 times, which translate into an 100 times speed up in the number of experiments, because if you wanted to improve your error by 10 times, you need to perform 100 times more experiments. So due to the intrinsic Gaussian noise in performing measurement. So yeah, so a key question is to better understand why by performing this derandomization, we could have an advantage in measuring Pauli observables, and how we could utilize this mechanistic understanding for designing better measurement schemes for more efficient estimation of observables. That's it for my talk, and thank you so much for listening.